Okay, so morning everyone. My name is Prof.Kato. So this is the third lecture, I think, in advanced courses on real-world data circulation. So welcome. So it's been a while since I met you guys, but maybe you don't know me very much. So I'm not a party guy. I'm information systems and working for computing systems, and may not be really related to data science, but it could be computing platforms for real-world data circulation. So I'm going to give a talk on autonomous vehicles, especially as part of real-world data circulation. So autonomous vehicles by literature, so it just drives by itself, a car, which I met in CMU. So I recommend you guys, sometimes if you go to, say, overseas and meet more, say, cutting-edge research projects, then it may impress you a lot. So Japan is really an advanced and a developed country, but if you go overseas, sometimes you see more. And in my case, it was autonomous vehicle because it was simple, right? It's a vehicle just drive by itself, but it's amazing because nowadays you have to drive your car, but it can, release your, say, save your time maybe in driving, and it's interesting. Just drive the car without touching the vehicle. First of all, so the autonomous vehicle is, I believe, somewhat related to data circulation, because today the car just drives, and the system is very closed. You cannot access to the internet by a car. You need to have some smartphones if you want to access the internet while you are driving. But in the future, I think it's going to be more open. And you can get data from infrastructure. You can get data from pedestrians, I think. And you can get data from drivers. And a variety of data can be uploaded onto cloud or the internet and do some analysis or do some management of data. Then you can feed back to the vehicle so that this guy get more, variable data. For example, you can predict where it's crowded, and you can also predict where some old people or kids may just appear. So you can prevent some exceptional accidents if you can guess what the world would be like in, for example, a few seconds or a few minutes. So this is what I want to do, and I believe this is really related to what you are studying, I think, in this program. In my case, do you know him? Do you know him? He is one of guys in this university, who have a lot of influence. And I met him 2 years ago, and I talked to him. Can we start some autonomous vehicles project? And he says yes, because he has something. Okay. Then once you find out, partner, so all you do, the research and development, it goes day by day. But you also have to think about how to demonstrate what you are doing. So this is some demonstration that I did only 2 months after we started. So I didn't have anything. But I did something to trick and to attract people. By the way, he's interesting. Do you know? So he's looking at some computer, but this is not his computer. He's pretending to, check the system But this is actually my student's computer, so he doesn't know at all what it's doing, but he's just pretend for a TV show. Very good. Hayashi-kun? 違う? 違う? So demonstration is important. Even though you don't have achieved anything, you can do still demonstration to show how you are planning to do this demonstration. And demonstration attract some people, then you can start something. And PhD project is kind of individual project, so you can work yourself and sharpen your skills and make some achievement, what you want to do. But if you are in a team and if you want to do some big project, you need to find some friends, teammates. And collecting teammates is it's time consuming and sometimes difficult, but just try to do it. And if you tell people what you really want to do, then sometimes people are impressed. Find more teammates, then that's fine. Now I have 20 to 30 teammates in a project, and I believe the scale of my team, one of the biggest teams in the world. So now we have at least human resources. I can be proud of my team, and a lot of possibilities that to produce cutting-edge results. So if you have teammates, you can do big things finally. And since you are students, you don't have to be leading this team, but it's going to be good experience for you to be part of some team and learn how to lead the team, for example. And if you have resources, then more resources coming to you. Now I have 6 vehicles. Since 6 vehicles cannot fit into the garage, I put 2 vehicles in outside. But now, we can do something similar to Google, just following what Google is doing, for example. But you should also have some new ideas, since imitating the existing technology doesn't really work for universities. So find out what is new ideas. So my case, I like hardware and supercomputing. So I have Jia here. She's working on many cores, not specifically for autonomous vehicles, but many cores. It's a emerging technology. There are 100 to 1,000 processing cores on a chip. It's very high performance. By the way, do you know supercomputers? Supercomputers, Japan has achieved twice the top 1 supercomputers in history. One happened very recently. You may know K, which is developed by Riken. But the other history we have is 10 years ago. There it's called Chikyu simulator, which was 1 kilo square meter. So it's almost the same size as Tokyo Dome and 6 megawatts. I believe if we have such computer, we can do, say, autonomous driving by thinking like human. It's artificial intelligence. Somebody may say it's impossible, but I believe it's possible, because if 10 years have passed, then you can build, for example, the same system as 10 years ago by, say, in this case, box, which is 1,000 times smaller and 3,000 times more energy efficient. So if this performance trend or this power trend will continue, then I believe the computers in, for example, smartphone can have almost the same performance as a supercomputer 10 years before. And if you look at industrial trend carefully, again, if you don't have knowledge in computer science, you may think that this may not happen. But if you have some knowledge in computer science and do some investigation, you can find that this is possible. So knowing something outside of your expertise is also important. Because in my case, I don't know automotive systems at all. But when I look at some trends, I found out autonomous vehicles, and I found that my expertise, which is computer science, can contribute to autonomous vehicles a lot. So knowing a variety of areas is really important. Okay, so sensors may be interesting to you because sensing is one of the topics that you do in this program. And I use, maybe you guys know cameras, which are the most familiar sensor. And I also use GPS, which is actually called GNSS. So GPS is American system. GNSS is a general name of GPS. And what I want to stress on this slide is this guy. So this guy is really, really functional, highly functional. So Google is using, and some car makers also using. And universities, a lot of universities around the world, they also use this sensor. This is expensive. So that's why you need a rich leader asking him to buy one. If it works, asking another one, another one, another one. And sensing is a hybrid of information science and engineering. When you buy sensors, you have to install them to the target system. In my case, which is vehicle. So my student, so every time we start some experiments right on top of the vehicle and attach the sensor to the vehicle, then finally we can start the project. We did this installation every time for 2 years, but finally we got a garage, so we don't have to detach the sensor every time. So we detach the sensor every time because I don't want it to be stolen. We have garage, can be locked, so we don't have to detach the sensor. But anyway, some engineering happens if you work on data. So sensing is collecting data. And you may think that since you are in information, measurement, then you can assume that data already exists there. But maybe sometimes it's good for you to collect data yourself. I think we did in Data Tools Next, using smartphones and get some GPS information. That was a good example of collecting data. But if you look for the real world, there are more case studies. For example, this is scanning sensor. This scanning sensor can be physically attached to the target system. This is amazing because you don't have to write single line of code, but just attach the sensor to the vehicle and download some software and click some button, then you get this information of data, which is three-dimensional real-world information obtained in real time. And this is called laser range finder or LiDAR, laser LiDAR. There are a lot of names that represent this sensor. But this is one of amazing sensors that I have ever used. So we want to use this kind of data for something innovative. One actually first thing that came into my mind is that to detect your location using this sensor. So again, this is the problem of managing data. My case, we use a digital map, three-dimensional maps. This is a collection of points. And if you store this data into your computer, then you can manage, for example, the shape of road, or the shape of buildings, or the shape of actually the real world in a computer. Since this is three-dimensional, you can, for example, change the angle of the data. So this is amazing to me, since I was not very familiar with data management. But when I asked some company to make the three-dimensional map of this is Motoyama Road, then they just gave us this map. So it was surprising to me, this is already possible in industrial service. And once you have three-dimensional maps, and you also have sensors. So you have data, and you have sensors. If you, say, do matching of real-time sensor data and map data, then you can find where you are at. Say, real-time sensors can obtain the shape of your surroundings in real time. And you also have three-dimensional maps. You can find where is the most matching place to the data which you got in real time from sensors. Then, for example, hey, we are here, which is called scan matching. And this works very well. So this is our test course, and we made a map of test course. Then check where you are driving by using real-time sensors. By the way, this is made by Kitsukawa-kun, one of my leading students. And we can actually locate your position within an area of 10 centimeters. It's really precise. If you buy expensive GPS, which, for example, military is using, still you can only detect your location within an area of 1 meter. So using sensors and three-dimensional map, then you can get for almost 10 times more precise localization or positioning. And it didn't really take so long time for Kitsukawa-kun to make this movie, because we have a lot of tools, software. Then, since you have in a big team, if you ask your colleagues for, say, what kind of software, what kind of tools would be useful for doing this, so everybody can tell you. So you can save your time to build this kind of system, compared to the case where you just work alone. So that's why I also recommend that you work with some people, so you can save your time. And once the experiment in test course is succeeded, the policy of my team is that hey, let's go for the real world. So this is the real world, and actually not in daytime. This is almost midnight. Cameras cannot see anything, but this sensor is intelligent. It doesn't get affected by darkness. It can still detect where you are. So even in midnight, you can drive autonomously, recognizing your position precisely. So the question is, I don't want to ask every time some company to make a map. So I asked Kitsukawa-kun if he can build three-dimensional map by himself. And he spent a couple of months, and he can actually did it. So it is also supported by a lot of teammates in my team. Since you know where you are very precisely, you can just keep collecting the data from sensors. And if you keep collecting three-dimensional data, then just wait for a few minutes. You have this. You have this. And you have this. So when we asked the company to do this, it took a month. But using, say, information science or information engineering, cutting-edge technology, then it took only 3 minutes. So this is going to be good collaboration between maybe university and company, because the company was surprised by this demonstration, since they take every time 1 month to build a map, but Kitsukawa-kun just did it for 3 minutes. So now we are planning to, for example, sell this technology as a product. Since you are a leading program, in a reading program for industry, so maybe good experience for you guys to find some companies which can collaborate with you. Then try to make a service together, and you may be very happy if your skills and if your research project can be translated into the real world. So what the company wants to do is something like this. The company has a dense, precise map, which they developed, taking for a month. But sometimes the map is not complete, so we can complement this three-dimensional map by using real-time data. So, and to make this map, the company actually uses specialized vehicle, which cost $3 million. So they don't want to bring $3 million car to make a small space of map, because it's very risky. So we can use maybe less expensive sensors to complement the data. So this is the maybe final thing that I can introduce. So this is also made by Kitsukawa-kun. Since this map data is heavy, it's going to be a few hundred megabytes, or could be 1 terabytes, if you want to cover the whole area of, say, this is Moriyama district. So the idea is that you only need limited space of three-dimensional map, which you are driving, and you can update. Since you know where you are driving, you only need data, for example, in the range of 300 meters. So you can keep updating the data and kill unnecessary data, so that you can save a huge space of storage and memory, but still can do the same thing. So this is, to me, a new idea. Just using three-dimensional map and using real-time sensors to match your position may not be really brand new, but kind of updating. So we call it point cloud, by the way, point cloud. It's a point cloud. And updating point cloud data is, as far as I know, there is no technical papers yet, so which can be a research project and research publication, which we are working right now together. Now let's switch. Since I'm talking about autonomous vehicles, location is not everything. Once you got your position precisely, what you want to do next is to detect your surroundings. And this is Abraham's project, detect vehicles or pedestrians in real time. I can skip some details, but we use traditional approaches to image processing, but we use, for example, GPUs. GPUs are special devices that I just showed you in the early slide. So it has more than 3,000 processing cores on a chip. So it's high performance as compared to common CPUs. And in most cases, we can get improvement in performance. So since image processing is a time-consuming job, if you use, say, your laptop or desktop PC, and it doesn't finish, say, in a second, it takes more than a second for some cases. Since, say, you know for loops, right? If you do programming, you do some for loops to do some repeated processing, but it takes so long time. But if you have 3,000 cores on your system, you can reduce the time of this repeated procedure. But anyway, this is detailed, so I can skip it right now. So image processing is difficult in the sense that it needs performance, but it needs quality at the same time. And so Abraham find out that if we compute every single frame, every single image, then some misdetection can happen because this is image processing, and it can never be perfect. So it can never be perfect, but we want to make it improved. And what we did with Abraham is that we use the information from previous frames. Since we know that in previous frame, for example, this car is here, so we can predict how these cars can move in the next frame. Then, which results in improving the quality of detection. I think he used Kalman filters, and this is one of famous filters, and you may also have studied in your classes last year. So what you are studying in this program is also useful. So you should be happy that typically you cannot learn everything in the same program, but you learn a lot of skills in the same program, which is a good opportunity for you guys. Since when I was a student, I didn't have such a course, so I had to study myself. But now you have a rich program, and a lot of professors can teach you different skills. It's Kalman filters applied for moving object tracking, which is done by Abraham. And I have, of course, other students outside of leading program. So I often make collaboration of leading students and other students as well. So you remember the real-time scanning data, which is three-dimensional, which provide you three-dimensional information. Now you can put this three-dimensional information onto the image, so that the image has now information of, say, image by itself only has x and y. So even though you detect the vehicle, you don't know how far it is from yourself. But if we call it sensor fusion, combining different data into the same target, which is called sensor fusion. If you do sensor fusion, you have some information which originally was not provided. So in this case, the image has distance information, which was carried from scanning sensor. We need a calibration. Calibration is that to match the coordinates of different sensors. In this case, the position of camera and the position of scanning sensor must be synchronized, must be calibrated well a priori. But once the coordinates are, calibrated, you can do this. Now, when you detect the vehicle, you have distance information. And distance information is important for autonomous vehicles because you want to stop within some particular distance against the vehicle. Oh yeah, still, it's not perfect. There is some still misdetection, so which must be addressed by introducing more new ideas, which I expect Abraham to improve it. This is another interesting idea of using different sensors. So you have image, and you know your location precisely thanks to real-time scanning sensor. And I said that we have a three-dimensional map already in your system. So you can put the map information onto the image. So we don't detect lines by itself. We just bring the information from the map to the image. Then you can even find where the traffic lights are. It's difficult. Yeah, here. You know where the traffic lights are on the image. If you don't have sensor fusion, if you don't have different sensors, you can do this by only image. Sometimes not productive because image processing is by itself, it's a heavy, time-consuming task. Maybe we want to focus on just detecting moving objects by camera image, and other information we want to map from the map. Don't have to detect by yourself. Just look at the map and put the map information onto the image. Then you know traffic lanes, you know traffic lights, you know traffic zebra zone, and so on. So there are more data issues, like say, I like to use smartphones because it's easy for students to start with. So in our system, we use smartphone car navigation software. Since we have, rich system, now a lot of companies want that system. So if I ask some navigation company, if you give me the source code of your product, then I can let you use our autonomous vehicle system. So it's a good negotiation. Now we have a source code of car navigation, and we can modify it to connect to our autonomous vehicle system. So you don't have to, say, draw a path by yourself. Just you can choose the destination, and you can choose the source location, and use car navigation's function, and get the route. Now our autonomous vehicle can just follow this route. So it's now total solution, not only individual technical components, but now we have kind of whole total solution in the system. Or I can skip how the car navigation can be merged into the system. But what I want to talk to you is that now we can even combine smartphone application to the autonomous vehicle. This is not really, well, but still. So this is, once we get a route to the destination, now you can just follow this route. And so now, it's our time to search for some papers, to check the distance, and to check the route. So now we have a route. So now we can just follow this route. So it's now our time to search for some papers, to check the distance, and to check the route. So now we have a route. So now it's our time to search for some papers, to check the distance, and to check the route. So now it's our time to search for some papers, to check the distance, and to check the route. to find what kind of algorithm is good for tracing the route. And we found some famous algorithm, which was presented by CMU, one of the top schools in the world, which looks like very reliable. So we adopted this algorithm and implemented in a system. We can skip for details, but what we are doing is just assuming that this is a route and put some points every 1 meter, for example. Then just keep following these points. Maybe difficult to look, but so this green line is a route, and this blue point is the target point that the vehicle is moving forward. So just keep updating this point, the vehicle just following it. Then it reaches the destination. It's kind of easy idea to get to the destination. And of course, if pedestrian or moving vehicles are on the way of your path, then you have to change this path dynamically to avoid the moving objects. So now, as I said, the students are working on individual components like localization, object detection, and so on, and computing platforms. But as a team, we are collecting the whole, functions into one system as a total solution. Then now, maybe this is too details for you because you may not have computer science background, but this is the total system that we have. Hardware, software, applications in a vehicular system. And we also do some projects to interact with humans and pedestrians, then collecting these pieces of data in a cloud or the internet system. And since we are computer science, I like to focus on security and safety and performance, power, reliability, and so on. And my expertise is software. So we design the software to achieve the autonomous vehicle. Sometimes, say, we didn't have, say, control function, but we design a software first. Then, according to the design, we organize a research project. And now we are adding more functions to the system according to the design. And what I'm going to talk in the last slide is that so this is local system. It's a vehicular system. But since we have internet today, maybe you want to provide some useful information from the vehicle to the internet or from the pedestrians to the internet. And we build such a system. So now, not only the closed vehicular system, but also it's open system, including the internet and pedestrian and vehicles. So for instance, localization of moving objects may not necessarily be done in a car. Maybe we can do this localization in a cloud so that we can manage the locations of whole moving objects ultimately. And I think Google is oriented on that kind of approach. They want to use cloud or the internet to collect data and manage everything cloud, then feedback the results of computation or feedback the results of data processing to each client. And I like to build that kind of system as well, because if you focus on a vehicular system, then which is nothing different from what the car companies are doing. So I want to introduce more different view of ideas to, for example, car companies, which are my collaborators. And one of such ideas maybe comes from using internet. And say we have vehicular system which is equipped to send data to the internet. Since we have smartphones everywhere today, we can use smartphone connecting the internet by LTE or 3G, 4G. And collected data can be sent to the smartphone within a car, and the smartphone can send it to the internet. Now we have a small PC clusters. It's a collections of PCs in a lab and receiving the data from the real world, then keep storing in a supercomputer in Nagoya University. By the way, nobody knows that I am keep storing the data in a supercomputer. So I pay some cost, but maybe I'm storing more data than I paid, but nobody just realizes it. So maybe I'm looking for somebody to realize it. Then I just say, oh, sorry, I didn't know. Anyway. So here is one of demonstration that about what we can do if we have a lot of data. So this is actually done by Patty. You know Patty, right? She was a lecturer of Data Tools Next. So she's making some data management system, collecting data from, actually the data set comes from some past project, but she's generating the same data set in real time to the database and visualize them on central server. Now we can look at, say, some person is, say, moving on a particular place, which may be useful to predict where we will be crowded in a few minutes or a few hours later. If you can predict traffic jam, you can change the route so that the whole traffic system can be more efficient. Since traffic jam spend a lot of money, traffic jam spend a lot of time, so traffic jam actually can be avoided in most cases by knowing the locations of moving objects. So this is one possible application of managing data from the real world. So since this is two-dimensional map, which is actually Google map, and now we want to use three-dimensional data, the same information of moving objects, but plotting on different maps, which made by ourselves. So it's three-dimensional maps. We exactly know where is the lane. We exactly know where is the, say, traffic light and so on. We need to improve, we need to actually analyze and collect the location of moving objects, because these data sets just come from the smartphone, for instance. But smartphone GPS is not precise at all. So we may want to use some data analysis techniques to collect the positions of moving objects so that it can be more fit, on actual place, but which is in work in progress. So we're going to make maybe intelligent filters to collect the positions of moving objects so that we can totally understand, how moving objects will be moving in the future. So predicting the future is important for intelligent systems. Since this is human can easily imagine what would happen in a few seconds, but for computers, it's difficult for them to predict what would happen in the future. So we need a lot of, I think, research projects to make intelligent data analysis techniques. For my case, it's autonomous vehicles. And I like demonstration again. So since I have smartphones or tablets, I don't have to touch the vehicle to drive the vehicle. Just 3 clicks, then your vehicle is driving. I keep tension because may get something bad, but I pretend to be very safe. So it's for demonstration. And if you look at this video, it looks like this technique is interesting and useful for the real world. But for us, keep tension, because once bad thing happens, then the project may finish. So the demonstration is kind of risky. It can attract the people, but if you fail in the demonstration, you may lose some people. So, but I like demonstration anyway. And recently, we are now doing experiments on a public road. This is Moriyama district, and we just drive, not touching the vehicle, but understanding the location of the vehicle autonomously and control the vehicle, then, for instance, stopping at the traffic light. If you do this without telling the police, you will be arrested because you violate the regulation of law. So what I did is talking to the police for 1 year and try to make them understand this is a necessary experiments for the innovation, and this is not dangerous. Might be dangerous, but just tell them this is not dangerous. And if you let us do these experiments, Aichi Prefecture will be, getting more attention by other prefectures. So something like that. And now we are getting used to the experiments, even though there are plenty number of vehicles driving nearby our vehicle. This is our vehicle. We can still do autonomous driving. And it looks like driving slowly, but it's just because of them. I realized that in Nagoya, people are driving a little bit fast. So it looks like my car is driving slowly. But this is 40 to 50 kilometers per hour by autonomous driving. Now, if you keep demonstration, somebody reaches you. This is Terebi Asahi. Say, since autonomous vehicles are not in a production yet, so it is a good topic for them. By the way, this is Subaru eyesight, if you know. And this is 2 years ago, or 1 year and a half, which was almost 6 months after we started the project. So we didn't have a lot of functions at this moment, but we tried to do demonstration again to make it looks as if we are already complete. Now more media just reach you, I think, if you succeed demonstration. And this is last month, I think. This is Tokai TV or Nagoya TV, I forgot it. And I did demonstration in front of 200 people, which was also impressing for media. And this is a scanning sensor, which is not familiar with them, so it's a good topic for them again. And this is the student. Student is happy. He's showing on the TV. He can tell his parent, hey, I was on a TV, so I didn't waste your parents' money. Just, what he's doing is more kind of attractive for public people. This is a good thing for students, I think. newspaper. A lot of good say demonstration. So once again, demonstration attracts the people. So I think, of course, technical development is important for you guys since you are students, but you should keep thinking about how to demonstrate, how to present your results and present your ideas and present your skills to attract the people, or otherwise your useful techniques may not be appearing in the real world. So this is what I wanted to do. I wanted to talk. And all this happened just 2 years since I started the project. Since you have 4 years, I think you can do much better job than mine. Maybe you are on newspapers, you are on media, presenting your skills and presenting your ideas to the public. Then finally, providing the results of your research to the public is really important to, say, evaluate the value of what you are doing. Value is not determined by yourself. Values actually can be evaluated by some other people. So just presenting, demonstrating your ideas to the public, I want you to keep in mind while sharpening your technical skills. Okay, so once again, I want to do this thing, not only vehicle, but also kind of introducing different views of, say, the real world. Like we can get data from everywhere. Like in my case, I'm getting data from infrastructure, I'm getting data from pedestrians, I'm getting data from drivers and vehicle itself, and do some analysis, online, offline, whatever, then do feedback to the autonomous vehicle to make him more intelligent. This is what I can teach you, how the data circulation is related to the autonomous vehicles. Actually, not only autonomous vehicles, but also any robotics, social robotics applications may appreciate the data circulation. That's what I believe. Okay, so, and also, this is the last one, but having the vision of what you're doing is also important. Like, if you don't know how useful is your skill or is your research project, then you may be lost at some point. Just keep having some big pictures and keep having some clear vision of how your skills and how your research project can be useful for something. Could be society, could be humans, could be life, anything. But you have to keep in your mind that how your research projects can be useful for some applications. That's what I wanted to talk to you. And this is Nagoya University's, say, a concept of social driving, not only on the internet, Facebook or Twitters, but maybe moving objects can also connect to the social networks and exchanging some information. Okay, I think I have 20 minutes to go, but maybe we can just finish. And I was going to take you to the lab, but I think it takes some time, so I can just finish right away. Instead, I can get some questions if you have. Okay, thanks. いいですか?
Just one question.
Sure.
There's such kind of system used in commercial airplanes, navigation system in commercial airplanes. As you know, most of the airplanes, even while takeoff and landing, they don't depend on the pilot.
No.
They depend on a pre-designed system. Have you tried to compare between this system and the system you're doing?
So avionics, it's almost the same in the sense that the control is automated. But taking off and landing, the control is more, I would say, tight. Like it needs more, it's more like routine. It's not dynamic at all. It's, you have a specific place of where you want to land or a specific place of where you want to take off. The control is very tight. So in a sense that the control is tight, we need a different, say, techniques to solve the problem. But in case of vehicles, are more open and dynamic because you don't know where you are driving. So if the airplane is going to be automated fully while they are flying, then we may share the same ideas. But I think even, for the sky, I believe it's more less regulated than the public road, because in the sky, you don't have humans, you don't have buildings, you don't have traffic lights. So I would say, in the sense of automation, as a result, I want to say that it's a different system at all. But automated control may be similar, but understanding the real world, it's a very different challenges for autonomous vehicles rather than avionics.
Sorry, actually I meant like especially on takeoff and landing at airports, because I think it's kind of similar a little bit to the, especially at big airports, like let us say Canada or Heathrow in England. Like every minute you have a takeoff and landing, and it's kind of hard to control it. So of course in the sky it's totally different. Like at altitude, the obstacles that could face the airplane is totally different. But I mean, while takeoff and landing, it's also automated.
So
in that sense.
again, landing is, say, it's tight control. So you know exactly where you want to land. But for driving, there is no kind of specific points. Like every day you drive, you have a different environments. But for the airplane, well, could be different, but the most important thing for avionics is to guarantee the safety and to guarantee that where you are landing is the expected point. But it doesn't need, say, 10 centimeters accuracy. It can be 1 meter, or what could be, as a global position. Only for the moment that it lands, it needs precise control. But when you are landing and after the landing, you don't have to understand your location by 10 centimeters. But the public road, it has only 4 meters width. So you need to maybe, if the area of location exceeds 1 meter, then you may be off the lane. So it's kind of scale of understanding the world is a little bit different in avionics and autonomous vehicles, and you don't have to, again, detect humans. You don't have to detect moving objects for landing. It has to be safe, or you have to guarantee the safety where you are landing. And after the landing, you have to make the airplane stable so that it can keep going ahead. So control is, again, the same, similar, but understanding the world, it's a different scale, I think. Okay? で、ここへ入っていっていいの？はい。はい、どうぞどうぞ。
Are there any advantage or original points comparing with other company autonomous driving?
I think we are.
And the second question is, in this lecture, you mentioned about the importance of the promotion. But actually, there are very minor research. It is difficult to promote the research. So how do I, how should I do?
So for the first question, maybe this is an advantage for us because nobody can do this. Because three-dimensional maps, which is minor, so not so many people have the three-dimensional map. And scanning sensor is also still minor. Only selected people or only limited community has the sensor. So maybe combining two and detecting your location by 10 centimeters, which almost nobody else can do. So I believe this is one of clear advantage that we can provide from our system. And also, we do this as a total system. I don't know any other institutes that do this whole system by the single team. Say some university does image processing, some university does some localization research, but as a total system of autonomous driving, I think only our team can take handle of it. And for the second question, I think if you're, maybe it's misleading means that minor means that you know, if it's really minor, then you don't have to do it, right? If it's minor in a sense that you don't have a lot of people, then this program is very useful for you to find friends or find teammates if they are looking for similar techniques that you have. If the research topic is minor, then I think you have to change your topic. But if it's just a minor community, then it's a good opportunity for you to find somebody who wants that technique. Like one specific example that I can give you is that speech recognition, maybe you guys are doing in a lab. It has, it's playing a vital role. It's playing an important role of automated systems because we use smartphones since we don't know how to do speech recognition or how to do face recognition. So we do touch interface. But if you have good interface for speech recognition or kind of human recognition, then you don't have to touch the vehicle. You can just smile or talk to the automated system. Then the automated system can react to your mind. They may take you to where you want to go. Don't have to put destination by text, just maybe speech, something like that. How
do you detect or utilize information from the traffic light or traffic sign?
Traffic light, say, so again, we know the location by 10 centimeters. And we have map information in your system. And you have image. And you can say, I think I can give you this movie. So we can plot scanning sensors information onto the image because scanning sensor and camera are calibrated, so they know each other, the relative position and relative angle to each other. So the scanning sensor's data can be mapped onto the camera. If you can do this, which means that you can map three-dimensional information to two-dimensional. Like scanning sensor is three-dimensional. Image is two-dimensional. It only has x and y. Three-dimensional scanning sensor, it has x, y, and z. So it can plot three-dimensional data. So say this case, red points means that it's far position, and blue points means that the close positions. So if you can do this transformation, then since you have a map which is structured by three-dimensional information, you can plot map information to the image. Say, what? So of course, say we know where the zebra, and similar to zebra, we exactly know where the traffic lights are. So it's already in the map. And the map has height information. So we can just plot the map information onto the image. So we don't have to detect him. Just plot.
It already exists in the 3D map.
Yes. So yeah, it's like pasting 3D map onto the image. Then you know where exactly the traffic lights are. But calibration is difficult. I think this is data analysis topic as well. You can see that a little bit error in calibration. Traffic lights, I think I can show the next one. Say here. The real traffic lights are here, but the mapped or plotted data from the map information show up there. Since this is calibration error, if the calibration is perfect, if two sensors, scanning sensor and a camera, knows the difference in angle, difference in distance to each other perfectly, then those pieces of data from the map information must exactly match the real world information. But so we want to improve it so that it can exactly match. So we don't
decide whether go through the clocks or not.
You mean green or red?
Yes, and sometimes we get confusing with whether we have to go or not.
Oh, I see. For traffic light is easy, right? If it's red, you stop, and if it's green, you stop.
But it turns yellow while we go into the.
That needs machine learning. So machine learning or rule-based systems are it's a natural language techniques, and often search engines like Google, they use rule-based systems. It's a lot of rules, like if traffic light is yellow, and if you have distance from the traffic light to yourself, if it's less than, say, 3 meters, then you can go. Or if it's longer than 3 meters, then you should stop. Something like that. You can write a lot of rules to decide your behavior. This is one approach, but the other approach is that we use machine learning. Machine learning is that you collect a lot of data from good drivers and just make the model of drivers, then just apply them to the real world, the decision. You don't know why you stop, but looking at the model, looking at the filters that you created from machine learning, it says just, hey, stop. So, and we don't have that skills yet. We have students working on it. So right now, we can only deal with the, say, easy scenarios. So if the traffic light is yellow, our car just go through. So we have to improve it, just according to how humans are thinking.終わりでいいですか？なんか質問があったら全然。一旦終わりにしますか？はい。いいですか？いいですか？ OK？ いいですよ。Okay, so thanks. Let's go for the lunch time.